Morning. We get to look at lesson 3 and 4, which are topics that get picked up in calculus again, specifically continuity, asymptotes, oblique asymptotes, horizontal and vertical asymptotes. Much of that is a big part of physics 30, math 31. In this course, we get to look at vertical asymptotes. Those are places where the graph has an infinite discontinuity or a point discontinuity leading to a hole in the graph. We're going to look at algebraic support for the concept. Um, and we've got a connection between rational and radical equations in this section. Rational functions are expressions that have polynomials divided by one another. And we want to look at the relationship specifically between the numerator and the denominator. So if you take a look at the note for my denominator needs to be greater than 0, or else I simply have a polynomial function. And we end up with problems with denominators. Remember, you cannot divide by 0, and that will occur here when x is equal to 1. It will occur here when x is equal to plus or minus 3, and it will occur here when x is equal to minus 2. Those values are referred to as non-permissible values, and we'll actually write them as x cannot equal 1, x cannot equal plus or minus 3, x cannot equal negative 2. It creates problems in the graph. Let's turn a few pages. I'll give you the page number. We're actually going all the way to page 460, where the encouragement is to perform our skills algebraically. So 460 skips some of these exercises, and here I am on page 460. So we want to take a look at rational and radical functions, looking for vertical asymptotes. Algebraically, you can find vertical asymptotes of rational functions by finding the zeros of the denominator, because the graph is undefined at those values. The equation will be x, the zero values of the denominator. So vertical asymptotes are an x equals statement. Horizontal asymptotes are a y equals statement, and they happen in a variety of circumstances. If the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is a horizontal asymptote. So the degree, remember, refers to the highest exponent in the polynomial. If the degree of the numerator is equal to the degree of the denominator, then the line y equals a over b is a horizontal asymptote, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. Again, in calculus, we play with this even further. And the last policeman statement, just slide that down. If the degree of the numerator is greater than the degree of the denominator, then the graph does not have a horizontal asymptote. So our calculators can help us algebraically. We can do it as well. Let's slide down. So I'm going to take a look at disassembling this polynomial in the numerator and the denominator. I'm looking for asymptotes. The first thing I want to look for is a horizontal asymptote. I see that the degree of the numerator and the denominator is the same, so I'm looking for a horizontal asymptote. And the suggestion is that it will be the coefficient of the numerator, the highest degree, the leading term of the numerator, and the leading term of the denominator, the highest degree. The reason this happens is that the x squared term in both cases actually predominates or overpowers the rest of the statement. So as x gets very, very large, or as x gets very, very small, you end up with essentially infinity squared, plus infinity minus 6 divided by 2 times infinity minus infinity minus 3. And I get the remaining concept if I can divide every term by x squared by that overpowering concept. So I'm going to take every term and divide by x squared. That's how horizontal asymptotes have been studied. X over x squared minus 6 over x squared divided by 2x squared over x squared minus x over 3. Make sure I'm recording. Minus x over x squared minus 3 over x squared. On your calculator, take a look at what happens when you have x over x squared, or when it simplifies to 1 plus 1 over x minus x over x squared, divide by 2 times 1 minus 1 over x minus 3 over x squared. The 1 over x or 6 over x squared term or 3 over x squared term, as x gets very, very large or as x gets very, very small, those numbers approximate to 0. Those numbers basically become 0. They basically become 0 approximately. They basically become 0. So I'm left with 1 over 2, which I suggest is my horizontal asymptote. Now we also have to look for vertical asymptotes. Vertical asymptotes come from the denominator generating a 0. So I've got to look at the denominator, 2x squared minus x minus 3. Two numbers that multiply to negative 6 but add to negative 1. That is negative 3 plus 2 and negative 3 times 2. And if I write it nice, 2x squared plus 2x minus 3x minus 3. I can factor in pairs. Repeat that x plus 1 term, which is my common term. I need a minus 1 sitting outside. So 2x minus 1 and x plus 1 are my factored forms. That suggests to me that I'm going to run into problems when x is negative 1 and when x is 1/2. Now, the one thing that we should check is what happened in the numerator. In the numerator, I could also have factored. So the numerator factoring is x plus 3, x minus 2, which doesn't cancel anything in my denominator. So I have 3 asymptotes to worry about. I've got asymptotes that are vertical, that the graph will not cross. And I've got a horizontal asymptote at 1/2. One thing to remember is horizontal asymptotes are reached at infinity. So horizontal asymptotes are reached at infinity. Asymptotes are reached at infinity. They can be crossed on the way to infinity. You'll see what that looks like on the graph. So that's lesson 3. I'm going to load up lesson 4 and we'll look at that today as well. Thank you.